Here's our mass on a spring, and we're going to set it in motion. I'm going to cause an extension, and now we have this vibrating motion. This is called a simple harmonic oscillator, and it's simple harmonic motion because of Hooke's law. Some definitions. An oscillation is the motion of an object that keeps repeating over and over. You know, this thing will keep vibrating up and down. It's often called periodic motion. That's the other word that's used for it. And these oscillations happen when there is a restoring force. Now here will be our equilibrium position. When we have a mass on, it's already stretched. That's our zero position. And at this point we say, okay, there's zero energy. That's our starting point. When I extend that down, that is an extension, as we've already seen, and there's now a force causing that mass to be pushed back up. That extension, that maximum extension, is called the amplitude, and there's a force pushing it back to the equilibrium position. And as it continues to bounce up, it squishes the spring, then the spring pushes it back down, and it keeps going. And one repetition is called a cycle. Another word you need to know. And the time to complete one cycle, or one repetition, is the period. You know that. The time to go up and down once is the period, capital T. And the frequency is how many times does it go up and down in a second, and that's, if it's per second, it's always called hertz, Hz. Now you need to know all of this stuff. So let's get our harmonic oscillator moving and then analyze it just a tiny little bit closer. Now this is because of Hooke's law. You have this restoring force acting, and it's linear. And let's look at what happens here. There's our equilibrium position in the middle, the maximum amplitude on top, and the maximum amplitude at the bottom. Now, let's look at how we can analyze this. We'll call this our zero reference point, and we're calling it our zero reference point even for energy. And so that amplitude is the maximum amplitude there, A, and the maximum amplitude there at the top. Now, let's look at what happens velocity-wise. As that mass is pulled down, the spring stops it, and it reaches a velocity of zero. And the maximum force now, there it is, at the maximum extension, is causing it to return to the equilibrium position where it will have a maximum velocity, right? There's no more extension. It's now back to that point. It'll have the maximum velocity, continues up, squishes the spring, and then finally, you know, it's got a velocity of zero on top again. And this restoring force wants to push it back down, and it keeps going. Now, from an energy perspective, the maximum energy will be right there at that equilibrium position, 1/2 mv squared. All of the energy, there's no more compression in the spring. That's because that's our zero definition point. All of the energy is kinetic, 1/2 mv squared. But at the maximum amplitude, the velocity is zero, and all of the energy is now stored potential energy, 1/2 Ka squared. And so at the top, likewise, the spring has been squished. Work is done on it, and you have 1/2 Ka squared for that system. That's the energy stored there, no velocity. So let's just review. Here it is. In the middle point, we're calling that, we're already extended as our 0 point. And the energy it has then, once this is oscillating, is the maximum kinetic energy, 1/2 mv squared. That's the maximum velocity. And the maximum extension, the velocity is 0, and we have 1/2 Ka squared. Energy is conserved. And so our first equation can be 1/2 mv squared equals 1/2 Ka squared. And this is a very useful formula to solve various questions with simple harmonic motion. Know how to derive this, understand the kinetic energy at the equilibrium position, and the 1/2 Ka squared at the maximum extension, and energy is conserved.